A warm welcome from ZIV to the first webinar in a series of 3 on the topic of active network management. My name is Bill Carlisle and I'm joined today by my colleagues Inigo Bilbao, who's based in Spain, and Graham McLean, who's also based in Australia. Graham will be presenting the ZIV webinar today, and it is called What and Why Do We Use ANM Systems and the benefits that we get from them. The webinar is scheduled to last 20 minutes with 15 minutes of presentation followed by 5 minutes of Q&A. You will note a chat facility on the right hand side of your screen where you can post your questions, and we will do our very best to answer as many as possible at the end of it. We will, however, be able to respond to all questions at the end of the event. So without further ado, Graham, if you could start your presentation, please.
Great. Thanks, Bill. Good morning, good afternoon, and good evening to everybody who's logged in to this webinar. What we plan to do today is to give you an oversight of ANM, what it's used for, what its needs are, and also how ZIV approaches the topic of active network management. It's actually quite a big subject, so we're have got very little time here to give you the full story. But what I'm trying to do is just to hit upon the main key advantages of ANM and how we deal with that. So what you'll find is, if you think back over the past decade, we've had a significant growth in the number of distributed generators that have been connected to the distribution network. This is something that's been happening, and it's going to continue. We're finding more and more our customers are having more and more distributed generators connected to their network. It's created all sorts of issues for our customers, the DNOs, because traditionally what you found is that the generation has been provided by few large generators located in particular positions, and the network was designed to handle these large amounts of energy and then to distribute it through the network. But now with this huge number of distributed generators, which are primarily connected into the distribution network, we're finding that these networks are not coping. They're having all sorts of issues, and we're having to address all sorts of problems that they were never designed for. And this is only going to get worse as more and more get connected. So in order to find a solution to this problem, the active network management system has come into the game. And ZIV has been one of the leaders in this field and then developed quite a complex solution for active network management. What I'm going to deal with today are just 4 of the main applications that you'd use in ANM, or DERMs. It's also termed DERMs, which is Distributed Energy Management System, which is the same system, just a different name. But you know, there's a lot of other. We're finding a lot of our customers are giving us a lot of other applications that we're having to solve for them as well. So first of all, let's deal with the need for ANM. Why do we need ANM? And what we need is to find a reliable and safe way of adding quantities of DERs to the existing network. As you add more and more generators into this distribution network, we're going to find that the network in certain areas is going to be overloaded because it was never designed for that type of load. And the network, the ANM system, therefore, has to identify and manage these network constraints. And the constraints that we find is things like your cables are overloading, or your your transformers are overheating and then overloading, and various other assets that are struggling because they were not designed to have large amounts of energy connected into the network as part of their network. So, and in order to, the obvious solution is to replace the cables and to replace the transformers, but of course this is very expensive. So one of the early needs for ANM is to delay the need for expensive reinforcement of the existing grid. So we can then add more and more generation. The ANM system will look after the network. It'll identify where the constraints are and make the necessary adjustments to the generation or to even the network itself if required, and resolve some of these situations. Another reason for the ANM is that it also gives the DNO an opportunity to ensure that the DERs operate within the grid code. Up until quite recently, there's been no control at all or monitoring of whether where the generator is connected, whether he's providing the power and the energy at the right voltage, he's providing the right amount of energy or how much energy he's providing. So with an ANM system, you have complete visibility of what's happening and what is happening at that interface between the DER and your network. So what are the uses of ANM? I've got, as we go more and more into this, we've got to find that the ANM system has to find ways to manage the thermal constraints in real time during periods of high generation, which is the kind of obvious solution. As you add more and more, your thermal constraints are achieved, and then the network, the ANM system must continually analyze the network and identify where these constraints are, and then carry out the necessary action, whether that's reducing the generation, reducing loads, or a number of different ways in which it can do this, and for various reasons as well, utilizing various strategies, which are also variables. Another important one that we're finding is that we also have to deal with managing high voltages. This comes about very often when we're in areas, particularly where we're having PVs, where there's it's a very sunny day. We've got a very high generation from our DER, but the demand is low. We found that it's either a very its local area is a very sparsely populated, and there's not much demand, and therefore the ANM system must identify this, and it must adjust the generation to cater for this, to ensure that we don't have these high voltages. Another one where it's used a lot is for dynamic voltage stability. And this is a continuous process where the ANM system will identify where we've got instability in the voltages, and it will adjust the reactive power compensation that we're getting from the generators. So it'll send out different set points to the generators and adjust and ask for more kilovars or megavars, just to adjust the network operation. And another big feature of it is to optimize the connection of DERs on the network. Not only do we want to get the maximum out of our generators by getting them to generate and provide as much power as they can, we also want to make sure that we're using the right generators, that we're not dealing with generators that are the most expensive or are the most inefficient, or are the least sensitive, which is one of the different ways in which you can identify whether which generator to adjust to reduce the generation. Our ANM system works out a sensitivity of each generator to that constraint. So if you have a constraint, you might find that with less reduction in generation of certain generators, you'll get a bigger change or bigger reduction in that constraint. Whereas other generators, you may have to have large changes in generation, but only achieve a very little benefit because it's further away and it's got a more of an interconnected network between it and the constraint. So there's a lot of decisions that have to be made in the ANM system to be able to select which DER. And this is something which is agreed by the DNOs. It's something we can change, and we vary it from customer to customer depending on what the requirements are. The other important requirement for ANM is that we provide, the ANM system provides the operational support for trading platforms. More and more of the generators are now on sort of flexible agreements where they're paid for the amount of generation or energy that they provide. And we've got to find a way in which we can manage this trading of generation. And the trading platform needs a tool to be able to identify what generation is available over the next day or week or whatever it is that you're looking at. And in order to do this, what the ZRV ANM system has got a predictor or a forecasting application where it's able to predict and forecast what the generation will be that will be available for the next day or week or whatever period you're looking at. The trading platform then, based on this information, goes out to the market, and it's able to get to sell this generation to the different generators, or the load actually to the different generators, and they are then able to bid on this, and then the trading platform will work out which generators are to be used for different parts of the network, or different parts of the period. This is then fed back to the ANM system, which then manages the generation and automatically dispatches that energy from the different generators as required, depending on the requirement. Not only does it then dispatch it and allow the different generators to provide their generation at the different times of the day, but it also monitors and logs what power they actually do generate. So it allows the DNO to do an audit of this is what we bought, but also this is what we were provided with, and then allows them to balance the books and to provide an efficient trading system. So it does get involved in all aspects of the network. So I thought, in order, now that I've explained some of the issues that we've got, it'll be interesting to identify or to know what the system architecture looks like, how a ANM system is structured to be able to deal with all these different requirements. So what I've drawn here is an indication of the way in which the ZRV ANM system is structured. In order to simplify the explanation, we've divided it into level 1, level 2, level 3. But these are just just our allocations, just to be able to identify which functionalities is located with which level. So we'll start with the level 3 controller, which is the largest. It's a full server-based system. It contains, it can contain all the applications that you require. It contains the network analysis engine. It contains the database of all the data that we have. It also has dashboards, which allows the operators to identify what's going on in the network as to what issues are happening and how it's responding to that. It also has dashboards which allow generators or DRs to look at their particular generation and what they are doing on the network. And so they've got just a small restricted look at what information is available. The data all comes from the existing DMS, EMS, or SCADA system from our customer. That's where the majority of the data comes from. So we're talking, when we're using a level 3 controller, usually it's a large network, and it's a large geographical area with lots of inputs. And so that's where we get our information. We normally utilize an ICCP link, which will interface that large data into our level 3 controller, which is located at the DSO control center. So it's nearby. It's kind of becomes part of that. There's advantages of having a separate ANM system and not including it into the SCADA system, which would just complicate it. And as I said earlier, majority of our customers have existing SCADA systems, and they don't want to throw them out or whatever. They want to reuse them as long as they can. So our system seamlessly will integrate with that. The level 2 controller is just a smaller version of the level 3 controller. It's got less functionality, of course, and it hasn't got all the visualization and the screens and the dashboards and the fancy information. And it's normally located in a primary substation. So it will then deal with the network related to that primary substation. It'll still have the load, the core components, which are the load analysis, load flow engine. It'll have some other minor, applications built into it, like N-1, N-3, and things like that. But it won't. It has a lot less functionality. It's designed to operate separately as a separate dedicated unit, isolated from anything else, or it can be incorporated with the level 3 controller to provide sort of fast acting functionality that may be required at a primary station to make rapid changes in the network. So it'll utilize its own capabilities, its own functions to do something quickly and then report back to the level 3 controller. And you can have a number of level 2 controllers sitting at various parts of your network as required, or you can have none. You can connect your level 3 controller directly to your level 1 controller, which is located at the DER connection point. So it's the interface that sits at the intake sub of any large wind farm or PV farm or anything like that. And it will monitor the power flow backwards and forwards. It will act, it'll issue set points to the equipment. It will allow, in the cases of emergency, if you have loose communications or something like that, it will have certain functionality built in, which will automatically adjust what has to happen to the DER in those occasions. We don't have to use the ZRV level 1 controller because, and in most cases, we're getting a lot of that information directly from the existing SCADA system. But we do recommend it because it means that our level 1 controller has got that certain intelligence that's built into it, which is known to the level 2 and level 3. So it means that in the case of an emergency, the level 2 and level 3 know what's going to happen at the level 1 controller. And as such, the system can respond a lot quicker and easier to the emergency that happens. So some of the key attributes that we have in our ANM system is that we want to make sure that it's an incremental types of flexible system. It must be able to work in very small situations like microgrids and small applications where there's less data, less functionality required. It must be able to be expanded. Either that small one can be expanded, or we can start off with a larger system which has got more data, more applications, and more points. So we can extend the same system, or it can become a large system which can handle a large geographical area, which have multiple applications, large databases. and it can incorporate, other medium and small systems as such, as required. So it means that customers can start off with very small systems if they're a bit nervous about getting into ANM, and they can build on that and develop it if they want. There'll never be a wasted product. It'll always be something that we can expand to a larger system. The other thing that we've strived very hard to achieve is to provide an end-to-end platform. It means that we can provide all levels of the ANM. We can provide the level 3, a level 2 for smaller, and we can provide the level 1, which is the field equipment. And we also can integrate that data, so it can either come through the existing SCADA, which is this gray icon here, and get its data, or it can come directly from the field equipment directly to the LT without L3 without the L2, or it can, we can incorporate an L2 in between, which will allow it to do some more functionality. So it's a very flexible design that we can offer. But of course, the heart of the whole thing is the real-time network analysis, the Nova analysis engine, which powers all the application and is the root or the core, the center core of our product. And if you look in all of them, each one has got that core application, which is our Nova analysis engine. And this is something which is quite unique to ZIV, that we utilize a real-time load flow analysis engine, which continually, as fast as the data that we get from a SCADA system, we can analyze that and identify all the problems that we talked about before, whether it was the thermal constraints, the voltages, the voltage issues or variations in voltage, all those things. It will work on constantly at all times, with typically we're talking sort of like 5-10 seconds here. It will carry out those analysis. The way that it works is that it will get its data from your physical data network, which is your SCADA system, or from your RTUs, or from whatever it is. It then integrates all that data into the network analysis engine. That network analysis engine works on your network. So we download your network model into the ANM system, and our system will then go through your network model line by line, feeder by feeder, and identify all the capabilities, whether they're constraints, whether everything is running normally and there's no issues with any of the devices. And it'll do this on a continuous basis, continually updating it. If it finds an issue, or if it needs some kind of special requirements, there's an algorithm block that's attached to it, and that algorithm is continually checking and double checking that there's no problems within that network, that everything is as it should be and there's no problems. If a problem is found, the algorithm will propose a solution, push it back into the network analysis engine. The network analysis engine will then go and check that we're not creating more constraints by making those changes. If it's happy and everything is fine, it will then send out and dispatch that new set point or that new information out to the network. Typically it'll come back out through your physical network RTUs and so on, and go back out into the field. So it's something which is continually working all the time. The variable part is the network analysis engine. The algorithm is a very standard functionality. We don't change that. So as you change the system and as your network changes, we put in the new network maps, and it allows the network would automatically change the network and allow and accommodate any changes that you've made, and it'll check for any constraints. So hopefully that's given you some idea. Last slide I've got here is actually a list of the applications. It's quite complex, but what are the main applications that we foresee that most ANM systems will consist of will be the real-time load flow analysis. It will be thermal and voltage violation detection. It will be rating analysis and contingency analysis. And we'll also have fault level analysis. These are the main sort of base applications that we have in our system. But of course, there's many more. So I think, I'm not sure how the time's going, but I think I'm probably over time. But
No,
I think I'll stop there and leave it to you.
Yeah, no, that's great, Graham. But for a subject which is quite complex, in the time available, you've really reduced it down to a great level of understanding. So I hope the audience has certainly been given a great insight into ANM systems and why we deploy them and the benefits that we derive from them. I'm very conscious that we are over time, but I think we should still have at least a couple of questions. And looking at the chat section, we have a first question, which is posed by Mohammed Dimi. Hope I've pronounced your name correctly there, Mohammed. But Mohammed says, and Graham, if you can be ready to answer this one, please. There is a view for the future of the power grids and distribution networks to work as smaller sections like microgrids. There has been a trial for running a microgrid in Germany. Can ANM deal and manage this type of network arrangement if it is going to be the case? Graham, could you comment on that, please?
Yep. Certainly. The way that our ANM system works is that it will look at, in a microgrid, what you're doing is that you're balancing your demand versus your generation. And so you have basically just a little network, which our ANM system will analyze, and it'll monitor the demand that you're requiring, and it can adjust the generation to provide that. And so it'll automatically do it. So, ANM is a very general word that's used for a lot of things. But definitely the algorithms and the load flow and the methods and strategies that we've got built into our ANM will definitely allow microgrids. In fact, we've identified as well that microgrids are a huge part of that, of our future. Level 2s are probably all you need for that. You just need a small level 2 type controller, and we can utilize whatever RTUs or whatever sensors and devices you have. Our L2 controller is derived from our standard primary RTU, so it's very good at interfacing. It has all the features of integrating with with all standard transducers, sensors, switches, protocols, everything are all built into it. So yeah, definitely.
Thanks very much, Graham. I'm just going to pose you with one more question now, because I'm really time is running on. But just one final question, if you wouldn't mind. Given that different countries run different regulations of how they operate their grids, Graham, how does this actually affect the use of ANM systems in these different countries?
Okay. This has been quite a lot of discussion has been around this, because we're finding that what's happening is a lot of the countries are in different stages of development of their renewable generation. We found this in the UK as well, is that we started off there were a lot of fixed connections where generators were encouraged to provide us whatever they could into the network, and the DNO was sort of required to absorb it and to accept as much as they can, and they would pay for it anyway, whether they used it or not. But as times are changing, we're finding now that there's more and more flexible type agreements that are being implemented in the UK, for example, which means that we can now use the trading platforms to buy generation from generators at different rates, and we can decide on how much we want, and we're able to turn down when we don't want to use, we don't need that generation, we can turn them down, and they've signed up for that. So as far as the ANM system goes, we build that into our algorithms in our applications. We get that information from the DNO as to how we would, how he wants to handle it, and we can deal with it, and we can decide on how to adjust the generation based on whether it's technical best or most efficient, or as I said, the most sensitive, which is closest to the constraint, or whatever. We can choose whatever reason, whether it's first in, first out. All of those different methods can be utilized and are available as standard features within the ANM system. So I think this is how you would cater for the different sort of strategies and ways in which the different countries work.
Okay, thanks very much, Graham. That's a very comprehensive answer. I'm conscious now that we have well and truly run over time, but just as a reminder, this is the first of a series of 3 webinars, and we have a further 2 which will be taking place. The one next week is on Thursday, the 31st of March, and that is about virtual power plant management. And we have the 3rd webinar will take place on Thursday, the 28th of April. And that is about ANM systems, whether you apply a centralized or a decentralized architecture. So if you haven't registered for these webinars, please do so on our website. And just as a final point, I'd just like to remind you that the Wind Europe event takes place next month, in which we are participating, and that takes place on the 5th and the 7th of April. So hopefully some of you on this call will visit us on the stand. So thanks very much for everyone taking part in this. Graham, a great presentation. And until the 2nd webinar next Thursday, I'd like to wish everyone goodbye for now. Thank you.